Imagine we have the square root of 64 divided by 4. Notice it's inside the root, so I can go ahead and simplify, which becomes the square root of 16, and the square root of 16 is 4. Likewise, I can take the square root of 64 divided by the square root of 4. That equals 8 divided by 2, and that also equals 4. So this example gives rise to a model that we can look at where we have any nth root of a over b. We can rewrite that as the nth root of a over the nth root of b, assuming what? Assuming b does not equal 0. Because again, we want to avoid dividing by 0 until we really start to understand what that means. And even then, it's kind of a complex, fun, fascinating idea. So the nth root of a over b, we can break it up. So 1, we have the nth root, add in there, of a over the nth root of b. So let's look at a couple examples of how this can play out. Let's look at the cube root of 16 over 27. Well, let's break that down. So I have the cube root of 16 over the cube root of 27. Cube root of 27 equals a 3. Cube root of 16, no, 16 is not a perfect cube, but wait, one of its factors is. So I could rewrite it as the cube root of 8 times a 2. And then let's work our way back down here, do the next line. So I'll just rewrite it. So I have the cube root of 8 times a 2 all over 3. That equals the cube root of 8 times the cube root of 2 all over 3. And then lastly, the cube root of 8 is a 2. Cube roots of 2 all over 3. And there's my final result of learning how to divide a radical. Reduce this one or divide this. Well, right now, I can't divide what's inside too easily, but I can rewrite them as square roots over square roots. From there, I'm able to start to see some perfect squares pop on out. And actually, everything was already written in a perfect square if we're able to recognize that. The square root of x squared is an x. The square root of 25 is a 5. And the square root of y to the 6th, remember? What times what makes a y to the 6th? That's a y to the 3rd. And so these two rationals divide to a result of x over 5y cubed. And our last example of how exploring dividing radicals. Again, I can't perform the operation in the interior. There's nothing that divides well. So let's break them up into their individual roots. We have the 4th root in the numerator of 4th root of 7y to the 5th divided by the 4th root of x12, x to the 12th. The denominator is already in a perfect 4th form, so we'll leave that there for now. The numerator, I need to factor it into perfect fourths. 7 doesn't have any perfect fourths as a factor, so I'll leave it as a 7. Y to the 5th does. That includes a y to the 4th, and with 1 y left over. And then I have on the bottom, of course, still the 4th root of x to the 12th. In the numerator, well, let's don't do that yet. Let's write it down here. In the numerator, I have, what perfect fourths do I have? I have a y to the 4th. So the 4th root of y to the 4th is a y. The 4th root of 7 does not factor out or does not come out. And the 4th root of the last y. In the denominator, what times itself 4 times makes x to the 12th? And that's x to the 3rd. So now I am able to, or I have reduced that all the way down. Now, just as a side, if we remember, how do we think about 4x to the 12th? Because sometimes we still get kind of caught up on that. So what times itself? 4 times makes x to the 12th. Well, I claim x to the third does, because x to the third times x to the third times x to the third times x to the third equals, how do you multiply like bases? What do you do with the exponents? You add the exponents. So this becomes x to the 3 plus 3 plus 3 plus 3, or x to the 12th. Another way that you might be able to look at reducing that too, again, we've talked about this before, but it's a great time to remember, how else could that be written? Well, this is in root world. Let's rewrite it in exponential world. So the fourth root of x to the 12th can be rewritten as x to the 12th over 4. And how does 12 over 4 reduce? That reduces down to x cubed. So we see the fourth root of x to the 12th is equivalent to x cubed. So there you have it. Again, a little reminder sometimes, because this is something we forget. So it's good to be reminded.